Thank you very much.
This is the title of my presentation. In order to calculate building thermal load and energy consumption for residential and office building, annual weather data is required as an input data. For such calculations, standard weather data has been commonly used. Standard weather data is created by selecting a standard year having the average weather condition for each month and by connecting the selected monthly observation data. So standard weather data basically excludes extreme weather events. According to the IPCC 6 assessment report, under the most serious uh, scenario with the highest radiative forcing, the global average temperature for the period from 2081 to 2100 is likely to be 3.3 to 5.7 degrees higher than that for the period from 1850 to 1900. Due to the progress of global warming, recently, extreme weather events such as extremely hot days have occurred more frequently, and in the future, extreme weather events will likely increase further due to the progress of global warming. Therefore, the calculations of building thermal load and energy consumption based on standard weather data are not likely to accurate enough. For future or long-term building performance assessment, building thermal load and energy consumption calculations based on the data considering frequent extreme weather events are required. In this study, we developed annual weather data considering frequent extreme weather events. The target city is Nagoya, which is the third largest metropolitan area in Japan. Based on the progress of global warming, we considered hot summer and warm winter conditions for creating annual weather data. The final goal of this study is to develop future weather data considering extreme weather events based on future climate or weather projections. However, as the first step, we attempted to develop the method for creating annual weather data based on the past observation data of the Japan Meteorological Agency. And as a as an application example, we calculated the primary energy consumption for residential and office building model using the developed extreme weather data and com- compared the result with those using the standard weather data. As I said before, in order to create weather data considering extreme weather events, we considered the combinations of hot summer and warm winter conditions. First, we selected the candidate years for creating temperature criteria from the observation data for past 30 years. Next, we calculated the temperature criteria to determine the dates with extreme weather events for each month. Then we extracted the year having the highest number of the days with extreme weather events for each month, and finally created annual weather data considering extreme weather events by connecting the extracted monthly observation data. In the selection of the candidate years, we used the A1 values in equation 1 and the Fs values in equation 2. Here L means period for calculating air temperature, which is 30 years statistic data. The condition expressed in equation 1 means that the monthly average to daily maximum temperature in a year is higher than monthly average and 30-year average daily maximum temperature. In equation 2, under hot summer and warm winter condition, the cumulative probability function of daily maximum temperature in a year is generally lower than that 30-year averaged cumulative probability function. In addition, we introduced two conditions for calculating the FS values. We made the temperature criteria to determine the days with extreme weather events using mean value and the positive standard deviation of daily maximum temperature in the candidate years. For example, when the mean value and the standard deviation is 35.3 degrees and 3.0 degrees, the temperature criteria is 38.3 degrees. We introduced five methods for making the temperature criteria. Regarding the extraction of the year having the highest number of the day with extreme weather events, in these figures are for the month of August as an example. First, we counted the number of the days with extreme weather events from the data for August during the past 30 years. And next, we extracted the year having the highest number of the days with extreme weather events. In this example, it is 2000. This table shows the combination of the extracted years which has frequent extreme weather events for every month. And there are 10 combinations because we consider two conditions for calculating the FS values and five methods for creating temperature criteria. By excluding the same combinations, we created 7 annual weather datasets. For comparison, we also created a standard weather data using the same observation data for the past 30 years. As an application example of the developed extreme weather data, we calculated the primary energy consumptions for residential and office building model. This table shows the setting conditions for residential building model. And this table shows the setting condition for the office building model. This figure shows the primary energy consumptions for the residential building model. As I explained before, in this study, we created the developed weather data by combining hot summer and warm winter conditions based on the progress of global warming. And here, HS means hot summer and WW means warm winter. The results using the developed extreme weather data are these 7 results, and the results using the standard weather data is surrounded by a purple frame. Compared to the case using standard weather data, the increase ratios in the cooling period for the cases using the extreme weather data as 6 to 13%, and the decrease ratios in the heating period are 1 to 14%. This figure shows the primary energy consumptions for the office building model. And the increase ratios in the cooling period are 0 to 10%, and the decrease ratios in the heating period are 3 to 17%. This figure shows the differences in the accumulated primary energy consumptions during the cooling period, heating period, and 1-year period between the cases using the developed extreme weather data and the standard weather data for residential building. As we created the developed weather data combining hot summer and warm winter conditions, the accumulated primary energy consumptions during the cooling period increased by 6 to 8%, and those during the heating period decreased by 10 to 11%. However, in the differences in annual primary energy consumptions are within about 1%. And this figure shows the differences in the accumulated primary energy consumptions for the office building model. Compared to the case using a standard weather data, Accumulated primary energy consumptions during the cooling period increased by 6 to 7%, and those during the heating period decreased by 5 to 10%. Due to the long cooling period for the office building model, annual primary energy consumptions are calculated using the developed extreme weather data are 3 to 4% larger than that using standard weather data. These are conclusions. We developed annual weather data considering frequent extreme weather events using the past observation data, and applied them to the primary energy consumption calculations. For the residential building model, compared to the case using the standard weather data, the accumulated primary energy consumptions calculations using the developed weather data during the cooling period increased by 6 to 8%, and those during the heating period decreased by 10 to 11%. For the office building model, the accumulated primary energy consumption increased during the cooling period increased by 6 to 7%, and those during the heating period decreased by 5 to 10%. In the next phase of this study, we will develop future weather data considering extreme weather events based on the future climate or weather projections. Thank you.
Thank you very much. Have we got any questions from the floor? That was perfect timing. Yes.
Thank you very much. First one is about the extreme weather, you said.
Yes.